Hello everyone. In this video, we discuss how to evaluate classification problems, specifically for the case of logistic regression. In the simplest form, we have a binary classification problem, which means that the input is in the form of a d-dimensional vector. In other words, we have d input features, and the targets or labels are in the form of zeros and ones. We can think of these also as trues and falses, or positives and negatives. Therefore, the goal here is just to differentiate between two possible outcomes. And throughout this lecture or video, we sometimes call this 0 and 1, sometimes positive and negative, and that really depends on the context. How does logistic regression work? So the goal is to have a probabilistic model, meaning that we really find this probability of the label given the input vector and some parameters theta. So these are the parameters of the logistic regression. And since in this case, we only have two possible outcomes, we can model this using the Bernoulli distribution from probability, which means that in this case, we need to have one probability parameter, and that's the probability that y equals 1. And using the complement rule, we can find the probability that y equals 0. However, we have to be cautious here because if we use the linear regression model, where we find the weighted sum or the dot product between the input feature vector x and this parameter vector theta or weight vector theta, then we may not have a valid probability score or probability parameter. Therefore, the goal here is to translate these or transform this into a valid probability score. And we do this using this sigma, which we call the sigmoid or logistic function. The mathematical expression for sigmoid or logistic function for any input A is 1 over 1 plus e to the negative A. And here on the left side, we see the form of the plot of this logistic function. So here we are plotting this from -5 to 5. So we see that as a goes to positive infinity, this function approaches 1 since this e to the negative a goes to 0. And similarly, when a goes to negative infinity, then we have a large positive number in the denominator. So 1 over a large number, we get closer and closer to 0. And then we also discuss the fact that this is an invertible process, meaning that if I have the probability and I want to know what value of A led to that probability score, we can solve that problem easily using the logit function. So logit function is the inverse of the logistic function. All in all, what this means is that in the case of binary classification using logistic regression, we have this probability that y equals 1, meaning that the label is equal to 1, given the input and parameters, and this is the sigmoid or logistic function of theta transpose x, which is 1 over 1 plus e to the negative theta transpose x. And therefore, we can also find probability of y equals 0, which is 1 minus this probability. So now the question is how we can assign labels, right? Because right now we have probabilities. Therefore, in general, we have to use something called thresholding, which means that in the simplest case, or the kind of like the most typical case, we set the threshold to be 0.5, meaning 50% chance. So if the probability that that input vector x belongs to class 1, according to our model, according to our logistic regression model, is greater than or equal to zero point 0.5, then we assign the label to be 1, and otherwise we assign the label to be 0. So 0.5 is really nice in the sense that we are not favoring one of these classes over the other one. So having this information, let's go to the Jupyter Notebook and see how we can evaluate classification models. In order to explain different evaluation metrics for classification problems, we're going to use a data set known as MNIST, which is one of the most popular benchmark data sets in machine learning. So what is inside this data set? So the input in this case is an image. An image is a two-dimensional array, right? So we have height and width, and then we have the number of pixels. So in this case, each image is 28 by 28 pixels. But the nice thing is that we can work with this data set as a one-dimensional input feature vector, that x belongs to Rd that we had, by flattening or vectorizing these two-dimensional array. So this means that this 28 by 28 pixels or 28 by 28 array can be flattened as 28 square, which is 784 dimensional vector. So in this case, we put all of them in one vector or a 1D array, and that's the input representation for each image. And these values of these pixels in general, they are from 0 to 255, corresponding to different shades of gray. So 0 is usually considered the lightest or white, and 255 is the darkest or black here. And if you count here, we have 256 possible cases, which is 2 to the power of 8. So that's what we can do to represent these numbers using 8 bits. So that's like the classification problem we want to consider here. And the labels are the digit that that image represents, right? So each image is either 0, 1, 2, up to 9, right? So we have in general, in this case, 10 different classes. Although, as you're going to see, we're going to convert this to a binary classification because that's the main focus right now. And then in the next video, we're going to consider multi-class classification problems. And also for the choice of classifier that we have here, we are going to use logistic regression. And remember, when we say logistic regression, the main thing is the loss function that we use, right? Which is that negative log of the probabilities assigned to the correct class. And the other thing is that also very similar to SGD regressor here, we can use gradient descent, which is a very popular and generic optimization technique. So you can become familiar with the documentation here, but things that we really need. One is the choice of loss function. So if you scroll down, if you want to make sure that this is actually logistic regression, you need to use this log underscore loss. So that's exactly the cross entropy loss that we introduced in the previous video, which means that now we have a probabilistic classifier as we just discussed. And also we have other parameters too, right? So since this is based on stochastic gradient descent, so we have things such as learning rate. We also have different ways of changing this learning rate using the inverse scaling or other approaches. And also here you can have regularization too, right? So we discussed this for regression problems, the idea of adding a term to the loss function as a penalty term to control the complexity of a model. So this is very much something we can do here by adjusting this penalty term. So this is a very nice implementation of a classifier that can work with multiple loss functions, including logistic regression that is the main focus of this video. So in this case, let's import NumPy as NP. And also the nice thing about MNIST dataset is that there are multiple ways to import this dataset. But there's one way that is based on the scikit-learn package. And from scikit-learn.datasets, from this module, we can use fetch openml and give the name of this MNIST dataset. So here it may take a few seconds since this is a relatively like a large data set. And you can see that we have the data part of this in this data key and then the target part. And if I just look at the data part and the shape of that, you can see that this is 70,000 by 784. 784 is the number of columns or dimensions or features here because we said this is 28 a square, and 70,000 is the total number of samples that we have. So in this case, we have 10 different classes or digits, and there are 7,000 images per class. And that's how we end up with 70,000. And we can look at the targets or labels too, right? 504. So these are the digits that we have from 0 to 9. So one thing that we're going to start defining the data metrics and the target vector. So that's what we do here to find X and Y. Something that we need to be careful here is that if you look at the first element of this vector Y, you can see that we have 5. And before you could see that we have these quotations around here. So if you look at the type of this is something you can always do to find the type of any object in Python. You can see that this is actually a string, is not a number, right? So that's just something to keep in mind here. Okay. So with this, one thing that we need to do because we want to evaluate the performance of a classifier, we need to do train test split. We're going to use everything up to index 60,000 for training, and from 60,000 to the end of this sort of like array for testing. And you can do this because this data set has already been shuffled and randomly permuted. So this means that we can just start from index 0 to some index for training and the rest of them for testing. And then we use this dot shape to make sure that everything looks great. So we have 60,000, in this case, data points or images for training and 10,000 for testing. So we assume that we do not know the labels for these 10,000 cases. And then we're going to predict them and compare them with the ground truth. However, as I said, we want to convert this to a binary classification problem. And in order to do that, we put this condition here that whether the training label is equal to 5, and this should be a string as we just discussed, or it's not. So this case, if we just look at what we have as labels, this is true and false. So we can think of these as 0 and 1s, or again, like we can think of these as positive and negative. So positive is true, false is negative. It does the actual labels do not matter at all as long as we differentiate them. That's why we can think of these as different forms. And when we give this to scikit-learn to train our classifier, it's smart enough to know that these labels, as long as they're trues and falses, like here they're okay since they represent two possible cases, and there are no issues of passing this to a classifier in scikit-learn. And from here, we're going to import this SGD classifier. So that's the one that we just discussed. We also previously discussed this cross-val score, which is for cross validation, meaning that we want to divide the data into multiple folds and use one for training, and then the others for testing, and we repeat this process. And then we define our classifier and we make sure that to use the right loss function since we want to have logistic regression, maximum number of iterations, random state, etc. And then we want to look at the scores we get from cross-validation. So we pass in our classifier. This is the syntax, the training data, the X values, meaning that the inputs, the outputs for the training data, because we do know both inputs and outputs, and the number of folds for cross-validation, which we use 3 here. And then we need to have like a scoring system. Here we use accuracy, which is the simplest way of defining the performance of a classifier. So accuracy is the ratio of correctly classified data points, right? So meaning that if you have, let's say, like here, 10,000 total test data points, and 8,000 of these cases we do correct classifications, meaning that we find the correct label, then in that case it's 8,000 over 10,000, which we get 0.8 or 80%, right? So our classifier is 80% accurate. This one is very kind of like a natural definition of accuracy that we should be very comfortable with it. So let's see what the results are. So this may take a few seconds or so, depending on the speed of your computer, or if you're using Google Cloud. So you can see that, because what's happening here right now, right? We're having a relatively like a large data set, right? So we have 60,000 training data points, although we are using cross-validation, which means that we divide this into 3 folds. use one fold for testing and the remainder for training, etc. Okay, so we got our numbers, which are these are the accuracy scores. So we get about 96% accuracy, which is great, right? So 96% of the time, we correctly predict the label of test data points. And again, here you have to be careful because when we say that test data points, I mean in the form of cross-validation, right? So we have the entire training data that we provided, and then we divide this into three folds, one for testing, two for training at each time, and then we repeat this process so that we cover all the folds. Okay, so one thing we can do is to celebrate that we got a really good classifier because it is very close to 100% accurate. But let's define a very boring classifier, a classifier that we call it never five classifier. And as the name suggests, this means that every time that we want to predict a label, right? So this is the predict method of this classifier. We just provide a bunch of zeros and we convert this to Booleans, which means that we return false. So every time we ask whether this is digit 5 or not, we just say false, meaning that it's not digit 5. So let's look at the cross-validation scores for this new classifier on the same exact data that we had before, right? So the only difference here is that instead of this SGD classifier, we're using our boring classifier. And here immediately, so you can, since there's no really training here, you can see that we get results close to 90%. So what does this mean? So the reason that this is happening is because of the imbalance that we have in our data set, right? So when you think about it, so digit 5 is about 10% of all digits that we have, right? Because we have 10 digits here. So that's the 10%. So if we always make mistakes on digit 5 because we are never predicting anything at digit 5, that means that 90% of time we are accurate if we are looking only at the proportion of correctly classified data points. And so here you can see the big problem, right? Just by finding the ratio of correctly classified data points, it's very easy to ignore some of the classes that may not be well represented in our dataset. And that's a huge problem and the main focus of this video to figure out how we can properly evaluate such classifiers. So one of the things that we can do to measure the performance of a classifier, especially in a way that we can visualize the result, is using a technique called confusion metrics. So what is confusion metrics? It's very easy once I plot the result. You can see that it is in scikit-learn.metrics. And the way that this really works is that you provide the actual target values for the testing data points. So that's y test. And what we predict, this ypred5. So this is what we predict from our classifier. So if I run this cell, again, since here we have a relatively large data set, things can take a few seconds to run. So once we run this cell, we get something that looks like this. Okay, so what does this mean? So confusion metrics, the way it works is that in this case, we have two classes. So each row of this matrix corresponds to one of the true labels or true classes. And each column corresponds to a predicted label. So in this case, if something is negative, and again, negative, you can think of this as false, or you can think of this as zero. All of these are equivalent because there's really no numerical value here. These are just to distinguish between different classes. And when you work with confusion matrices, it's very common to think of these as negative and positive. So it's not necessarily -1 and 1, it's negative and positive. So everything that is from the negative class, which means that not digit 5, you can see they're mostly predicted as negative, meaning not digit 5. And this is what we expect, right? We have about 9,000 cases that are not digit 5, and we are going to predict them correctly. And we can do this because this is the majority or well represented class. However, you see the problem in the second row, right? So roughly speaking, we have about 1,000 data points that are from digit 5, meaning it's positive or true. But you can see that we are making a lot of mistakes because only 576 of them are correctly classified or labeled as positive, and a lot of them are misclassified. So in general, when you have a confusion matrix, you want to have things in on the main diagonal, right? So because this means that this first element here or location, that these are the data points that are actually negative and are labeled as being negative. So that's good. We want to have this to be as close as possible to the total number of negative samples that we have in our testing data set. And the same thing with this second location or the second element on the main diagonal. So the ones that are one or positive, we want to be actually predicted as being positive. However, these off diagonal terms are not ideal. To make this a little bit more formal, we can think of these as elements that we have in this location as true negatives, meaning that they're negatives and then they're also predicted to be negatives. So that's true negatives. Similarly, we have true positives. However, this term that we have here is what we call as false positive. This means that this was actually negative sample that is predicted to be positive. So if it's predicted to be positive, this is not correct. And that's why it's false positive. And the same thing with this second off diagonal term, right? So this was actually positive, but predicted to be negative, and this is a false negative. And by this categorization of these elements of this confusion matrix, now we can define multiple scores that they evaluate different things about our classifiers. The main ones that we use in machine learning are these two, precision and recall. So what is precision? I have these arrays for you to can easily visualize and come back remember this. So precision is true positive over true positive plus false positive. So if a classifier does not have any false positives, this precision is 1, right? So it means meaning that 1 is the best possible score if false positives are not existent in our classifier. And the same thing with false negatives, right? So that's what is measured by recall. So recall is true positive over true positive plus false negative, which we can also think of this as true positive rate. And if we call this true positive rate, then the opposite side, where we measure true negatives over true negatives plus false positives, is now, we can call this true negative rate. So you can see that we define multiple metrics here, but they're all kind of related and they depend on this, combination of false positives, false negatives, true positives, and true negatives. So this figure kind of like helps you to memorize or remember the connection between these different metrics. And now the question is how we can calculate this. Of course, you can always do this manually, right? So for example, here divide 576 by 576 by 47, and we'll see that there are built-in methods to do this. But one thing I want to emphasize here is the interpretation of this. So what does precision really measure or show us? So what this really does is that it tells us among all the samples that are predicted to be positive, what percentage of them are actually positives, right? Because we're looking at this column. And if you look at recall, it's the opposite side. It tells us from among all those samples that are actually positive, how many of them or what percentage of them are labeled as being positive, right? So that's the difference between this column and this row, because the column corresponds to all samples, if we add them together, that are predicted to be positive. However, if I look at this row, then if I add them together, these are all the samples that are actually positives. So one is predicted to be positive, one is actually positive. But if you want to find these scores, precision score and recall score, so we can just pass in two input arguments. the actual labels and the predicted labels, right? So with this information, you can form the confusion matrix and calculate these numbers. And if I print this information, you can see that here we have precision 0.92 and recall 0.65. And this tells us the problem here, right? So we have a very good accuracy in terms of precision because we don't have many false positives, but we do have a lot of false negatives, right? So that's kind of the issue here, having a lot of false negatives, which means that in this case, the denominator is significantly greater than the numerator, and that's why you get like something that is 0.65. And something to keep in mind is that usually when you have these complex problems, meaning that they are not easily separable, these classes, there is some kind of trade-off between precision and recall, meaning that you can increase the number of false positives, and at that cost, you can decrease the number of false negatives, and vice versa. And what this means is that in general, you cannot decrease them simultaneously. So when you decrease one of these two, the other one will increase. And this is something that you can measure using two different ways. So the simplest way is just something known as the F1 score. And what you do here is that you're going to find this harmonic mean, and harmonic mean is different than arithmetic mean, meaning that when you add two things and divide by two. So harmonic mean has this formula, 2 over 1 over precision plus 1 over recall. If you do a little bit of math, we can see that this is equivalent to 2 times precision times recall over precision plus recall. And F1 score is also always between 0 and 1, 1 being the best score, and 0 is kind of like the worst. However, the part that I really want to focus on is how we can find trade-off between precision and recall. And this is something that can be done using precision recall curve. So the idea is very simple. So since you have a probabilistic classifier, we can think of this probability that y equals 1 for an input vector x as this score function s of x. And we said that normally we set the threshold to be 0.5, right? Meaning that above 50% is class 1 and below that is class 0. However, we can change that threshold. So for example, if we change this threshold to be 0.9, what this really means is that we label a data point as being positive class or class 1 if we are very, very confident, right? Because now the threshold is 90%. So if this probability is greater than or equal to 90%, then we say class 1. If it's below that, then it's class 0 or negative. And what this really does is that it makes sure that we only have a few false positives and really reduce the number of false positives. And if we reduce the number of false positives, meaning that we find high precision scores, but that will increase the number of false negatives, which we're going to have low recall scores. And the opposite thing happens if we reduce the threshold significantly. So let's say you put the threshold at zero point 0.1. And this means that now a lot of these positive cases are very uncertain, right? Because now we have a very low standard to label something as being positive, which means that now you're going to have low precision and high recall values because false negatives are probably very close to 0. So you can do this manually, but again, thanks to scikit-learn, you can see that there is one of the metrics is this precision recall display. And here, since you want to change thresholds, you need to use from estimator, meaning that you have to pass in your entire estimator so that scikit-learn can work with different thresholds. And we give our classifier, the test data, and the actual outputs for that test data. So this model or this evaluation metric right now can find the probabilities for these testing data points, find the labels, meaning y-pred or predicted values, and compare them with this y-test to find precision and recall. And if I plot this right now, so you can see that this is the form of our precision recall curve. So on the y-axis, we have precision values. Let me zoom out a little bit here so you can better see this. So you can see that we have precision here, and on the x-axis we have recall. So you can see the trade-off here, right? So at some point, precision, right, is really, really high, but recall is very close to zero, which is here. And this happens for a while. And then we have this drop. So precision's now going to be closer to zero. And then the recall value is going to be closer and closer to one. So ideally, you want this figure to look like something like that. So you want to be close to this top right corner, right? That's a perfect case because it means that you can find precision almost close to one and recall almost close to one, which means that false positives and false negatives, they both are very, very close to zero. So that's the ideal case. But obviously, this does not happen here. And this red point that you can see here, these are the values that we find for our classifier with the default threshold of zero point 0.5. So meaning that this is the result we found before, right? Because I can show you what we have. Precision 0.92, recall 0.65. This is 0.92. This is 0.65 here. But we can change that threshold, for example, to be zero point 0.6, zero point 0.7. So each one will give you a different point here. So ideally, so one way we can summarize this entire figure using one single number is the area under this. And you can do this using different techniques, but the one that is implemented in scikit-learn is using what is known as average precision. So if I zoom in again now here, so what is average precision? It measures the area under the PR or precision recurve curve using this approximation technique. So what it does, so remember the precision values are on the y-axis and these recall scores on the x-axis. So you're going to find the differences between two consecutive values of recall scores and multiply them by the pi values. So if you have an ideal case where this thing is constant to one and then goes to so like zero at this very edge point, then obviously this will give you area one, and because the pi is always one, the precision value, and you're going to have these different segments on your x-axis, find probabilities, add them together. However, as you can see, when PIs or precision values are less than one, so you plug in these values here, and this summation will give you an approximation of the area under the PR curve. So usually for a good classifier or a strong classifier, you want to have values closer to zero point 0.9. Usually zero point 0.8 or so is considered a good classifier. But once you get to, zero point 0.6, zero point 0.5 and below, that means that your classifier probably is not that accurate. So I hope you found this video helpful by understanding precision recall and also precision recall curve, which is really nice. You get the full picture about your classifier.